To run a small generative adversarial network, also known as a GAN, written in Keras, using the major cloud providers such as Google Cloud Platform, Amazon Web Services, and Microsoft Azure, there are a few key components to understand. These include billing, machine types, available accelerators like GPUs and TPUs, supported frameworks, and how your code and data are managed in each environment. Starting with Google Cloud Platform, the preferred service for machine learning is called Vertex AI. Vertex AI allows you to train models using either pre-built containers or custom containers, and supports frameworks like TensorFlow, Keras, PyTorch, Scikit-learn, and XGBoost. If your GAN is written in Keras, you can simply run it inside a TensorFlow-based container without any modification. Your first step is to upload your training script, perhaps something like train.py, and your dataset to Google Cloud Storage, or GCS. Once uploaded, you can create a training job using the Vertex AI Python SDK or through the Cloud Console interface. Vertex AI supports a wide variety of machine types, ranging from general-purpose virtual machines like N1 Standard 4 to compute-optimized ones like C2 Standard 8. More importantly, you can also request GPU support, such as NVIDIA Tesla T4S, V100S, A100S, and others, depending on availability and region. If your model is designed for extreme scalability or requires high-speed matrix operations, TPUs, tensor processing units, are also supported, although they work best with native TensorFlow code. Billing on GCP is straightforward. You're charged based on the compute instance type, any GPUs or TPUs used, and the duration of your job. There are also charges for storage and data transfer if you're moving data between regions or out of the cloud. Now turning to Amazon Web Services, the main machine learning platform is called Amazon SageMaker. SageMaker supports most major machine learning frameworks, including TensorFlow, Keras, PyTorch, MXNet, and Scikit-learn. It provides managed environments where your code can run on dedicated infrastructure without having to manage EC2 instances directly. You start by uploading your training script and dataset to Amazon S3, which is AWS's object storage service. To train your GAN, you use a SageMaker estimator. The estimator lets you define the script entry point, the instance type, such as ml.m5.large for CPU, or ml.p3.2slarge and ml.p4d.24slarge for GPU, and whether to use script mode, which runs your script as is. SageMaker also includes built-in TensorFlow and PyTorch containers, or you can bring your own Docker image. You are billed based on the compute instance, storage used, and the time your job runs. GPU-based instances are priced higher, and usage is metered per second with a minimum billing duration of 1 minute. Moving to Microsoft Azure, the comparable service is known as Azure Machine Learning, or Azure ML. Azure ML supports a broad range of frameworks including TensorFlow, Keras, PyTorch, Scikit-learn, and LightGBM. You start by uploading your data to Azure Blob Storage, and then set up your training job using the Azure ML Python SDK or CLI. Your environment can be defined through a Conda environment file or by specifying a base Docker image. Azure offers compute instances through its Azure Machine Learning Compute clusters, which can autoscale based on workload demand. In terms of hardware, Azure supports both CPUs and GPUs, with machines such as the standard_NC6 for NVIDIA Tesla K80S, and standard_ND40RS_V2 for more advanced V100 GPUs. TPUs are not supported on Azure. Billing is based on the type of compute instance, the use of GPUs, the duration of compute time, and data storage. Azure also provides cost monitoring tools to help keep your machine learning workflows within budget. Across all three platforms, you can schedule jobs, monitor logs in real time, and even run hyperparameter tuning. All of them also offer free tiers or trial credits, so you can experiment before committing to larger scale deployments. In summary, whether you choose Google Cloud's Vertex AI, AWS SageMaker, or Azure Machine Learning, you'll be working with similar principles. You write your Keras-based GAN, upload it and the data to cloud storage, define the environment and compute power you need, CPU, GPU, or TPU, and then launch the training job. Your choice of platform may come down to your budget, your familiarity with their tools, or the specific performance requirements of your model. Registering the model. Model registration is the process of versioning and cataloging trained models. This allows you to track which models were trained, when, on what data, and with what configuration. This step is crucial for production-grade machine learning. Each cloud platform offers a managed model registry. AWS SageMaker Model Registry integrates with SageMaker pipelines, tracks model versions, and allows approvals. GCP Vertex AI Model Registry Supports automatic versioning and integrates with AutoML and custom model endpoints. Azure ML Model Registry lets you register, version, and annotate models. Models here can be deployed directly to Azure ML endpoints. Alternatively, for multi-cloud setups or on-prem environments, you can use MLflow, an open-source tool that provides model tracking, registry, and deployment capabilities. Registering your model makes it easier to roll back to a previous version. Tag metadata like accuracy, data version, etc. Control deployments, for example, only deploy approved models deploying the model. With your model trained and registered, you can now deploy it to serve predictions. There are two primary ways to deploy a Keras model. As a cloud-managed endpoint, this is ideal for scalable, production-ready setups. AWS SageMaker endpoint. Upload your model to S3 and deploy it via SageMaker, which automatically provisions infrastructure. GCP Vertex AI endpoint supports real-time serving with autoscaling. Azure ML endpoint offers real-time or batch inferencing with auto-managed infrastructure. These platforms handle requests, scaling, monitoring, and retries, freeing you from infrastructure management. Custom API using Flask or Fast API. For more control or edge deployments, you can serve the model through a Python-based API.